Hello everyone, my name is Grayson Duggar, and this is Physics 2212, Lab 4, Circuits and Capacitors. The purpose of this lab is to predict and understand behavior of circuits, both in series and parallel. Also, understand how capacitors and resistors function within these circuits. And then we are going to use an online circuit kit to model and measure the behavior of ideal circuits with these components. The modeling thing that we used was called the Online Circuit Construction Kit, and it allowed us to create a circuit and it will function as ideal. The physics principles used here were Ohm's law, capacitance, and Kirchhoff's laws. And the main result was that predictions made using physics principles matched the value shown in the online simulation, though real-world values would slightly differ. Ohm's law states that the voltage is equal to current times the resistance. Kirchhoff's laws are the node rule and the loop rule. The node rule that says the total current entering a node is the same as the total current leaving a node, and the loop rule states that the change in voltage for a round trip in a circuit is zero. And then for capacitance, we use the formula capacitance equals charge divided by voltage. There were two main simulations run in this experiment. In the first one, we were to predict/calculate the current at two different points of the first circuit, the voltage and voltage drops across this circuit, and then we were to make the circuit parallel and find the current change from the first series circuit. In the second one, we were to predict/calculate the time constant of the circuit. In these, the system was the circuits, the surroundings was everything else in the universe, and we were assuming that resistance in the wire and ammeters is negligible, and that our EMF or voltage was the voltage of the capacitors plus the voltage of the resistors. For the first part of the first experiment, we were supposed to assemble the circuit in the top left corner and then make a prediction on I1 and I2. Using Ohm's law, I got that I for both of them would be 0.0204 amps. And then when I actually ran the circuit, it was 0.02, which means that my calculations were probably right and the only difference was from decimal places. Then we were to replace the ammeter with a voltmeter. When I did this, the current in the other ammeter dropped to 0 and the voltmeter read 3 volts. This shows that there is an open circuit and that there is no current flowing through the ammeter. After this, we were supposed to calculate the individual voltage drops in the series, and so from CD, there was a voltage drop of negative 0.96 volts, and then for point EF, there was a voltage drop of negative 2.04 volts. This supports the loop rule, because it shows that it started at 0 volts and ended at 0 volts. Then I used Ohm's law to backcheck my work, and I got that the resistance of the first resistor would be 48 ohms, and the resistance of the second resistor would be 102 ohms. And I think that there are discrepancies from the decimal places in the original current that it shows on the online simulation. After this, we were supposed to make the circuit parallel and see what happened. When the circuit is changed from series to parallel, making an ammeter around the 100 ohm resistor, the current becomes 0.06 amps. This supports the assumption that the wires and ammeters have zero resistance. The path with the ammeter becomes a new path for the wire to take that circumvents the 100 ohm resistor, and it becomes completely neglectable. The new combined resistance of this segment, including the resistor and ammeter, becomes 0 because of the resistance of the wire and ammeter is 0. Then I used this to backcheck my work, and using Ohm's law, I got that the current was 0.064 amps. In the first part of experiment 2, we had to assemble this current using a capacitor and see kind of what happened. In the first part, the capacitor, when it was charging and discharging, the bulb started out bright but dimmed out as time went on. And then for 10 ohms, it took 9.2 seconds to charge, 11.2 seconds to discharge. Then for 20 ohm bulb, it was 18.6 seconds to charge and 22.4 seconds to discharge. For the second part of the second experiment, we were supposed to assemble the top middle circuit and use it to find the RC time constant using these fancy equations that we got. And after plotting this and plugging stuff into the equation, I got that the RC was approximately 5.984, which when we used our math and formulas, I got that the RC was 6, meaning that this was probably correct. Fortunately, there was no coding for this lab, which makes me very happy. And then for our what if and what if questions, what if you were doing this lab in real life and used an actual ammeter instead of a simulated ammeter? What's different about a real ammeter and how it affected the circuits you hooked it up to? A real ammeter still has resistance, so it is using an actual ammeter would lead to a lower current value than seen in the online model. Then, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this happen in real life? If this ideal situation were to be assumed, the capacitor would be charged in an instant. This would not happen in real life, though, as all parts of any type of circuit have to have some sort of resistance. That is all I have for my lab today. I hope you have a nice day.